So folks, what I'd like to do here is outline some of our properties of determinants. And these properties can all be proven, but in this case I'll just be stating them to you. The first one says that if we have an n by n matrix B and we get that new matrix B by multiplying a single row or column matrix A by a scalar k, then the determinant of this new matrix B is going to be related to the old matrix A by just the factor of k. So let's look at an example of that. Here I've got this particular matrix right here, 3 by 3 matrix, and if I want to go ahead and let's say I wanted to divide this column right here by the factor of 7. I notice that 7 divides into each of those entries. I can do so. I would just have to multiply 1/7 times the new matrix's determinant. So this would be 1 minus 1, 3, 15 minus 12, 9, minus 1, 1, 3. So again, folks, this is not a row operation. Don't confuse this with your elementary row operations from solving systems of equations. This is not a matrix that I've listed here, but rather taking the determinant of a matrix. And so computing this determinant right here is equivalent to computing this determinant right here, but then multiplying that result by 1/7. Another way of saying that is another way of working with this is I notice maybe now that I could divide this column right here, say by the number 3. So if I did so, I would factor out a 1/3 from the determinant. Careful folks, this is not scalar multiplication of matrices. This is my determinant computation, and I'm factoring a 1/3 out of this column, and this property says that this new matrix here that I'm obtaining will have the same determinant but just multiplied by a factor of 1/3. So that's where I get 5 minus 4 and 3. Okay? So now I can go ahead and if I wish, I could think about taking this row right here and dividing it by a 3, but then I would pull out another factor of 3 as I did so. And that gives me this new row of 1, 1, 1. Okay? And so again, what this property is saying is that I can divide out factors from individual rows or columns from particular matrices that I'm trying to compute the determinant of, and I can compute the determinant of that new matrix just by adjusting by this new factor here. Now, it may not be readily apparent why this is helpful, but notice that the level of the number of computations, the size of the computations that I would do in computing this determinant is quite a bit larger than this one. Most students would argue that I'd rather compute this 3 by 3 determinant here because it has all of these ones in it, as opposed to this one here, which is kind of heavy rich in factors. We've divided a lot of those factors out, and we've made the problem easier for ourselves. Let's look at the next example. So the next example is about interchanging rows and columns of original matrix A and noticing the effect that that will have on the determinant of that new matrix. So it turns out that if we were to take this original matrix A, in this case, for this problem here, we have that A is 1, 2, 3, 4. If we were to interchange, let's say we wanted to interchange to swap these the first column with the second column, it turns out that we can do so, but it changes the sign on the determinant. So let's do that here specifically for this example here. And so we can see that if I were to take and swap these two columns, that would have the effect of changing the sign of the overall determinant. So again, what we're saying here is that the determinant of the new matrix B would have the opposite sign of the determinant of the original matrix if I obtained matrix B by interchanging either 2 rows or 2 columns of that original matrix. For fun, we can look at this problem and we can keep going. Here we took the original matrix A and we column swapped 2 columns in matrix A, and that changed the sign on the overall determinant. Now what I'd like to do is, just for fun, let's go ahead and row swap. So if we were to do that, we could go ahead and row swap the rows of this particular matrix A. So we'd have 4, 3, 2, 1, and I obtained that through swapping rows. But if I were to do so, that would have the net effect of, in fact, here I better put a 1 here because I want to show that multiplication. That would have the net effect of again again multiplying the sign of that overall determinant by a -1, and just keeping track of our negative signs, we end up with the same determinant the same value of the determinant as before if we perform two column or row swap operations. So again, this property is saying here that if we were to interchange any two rows or two columns in a matrix A, and this does not need to be a 2 by 2, then that new matrix will have a determinant that's similar to the old determinant, just off by a sign change. This next property says that if two rows or columns of the n by n matrix are identical, then the determinant of that matrix is 0. So for this matrix here, we imagine maybe we've got matrix A in this case is the matrix 1, 2, 1, 2, and we notice in this case that column 1 is identical to column 2, and whenever a matrix that we're trying to compute the determinant of has equal, two columns that are equal or two rows that are equal, we know without computation what this property is saying, that that determinant will come out to be 0. In this case, we could easily verify this property by using our formula. So we could verify with the formula that if we were to take the determinant of 1, 2, 1, 2, why that's just, because it's a 2 by 2, we've got this handy formula for it. This row and column, or these two entries multiplied together minus these two entries multiplied together, 1 times 2, and sure enough we end up with 0. That seems very apparent just by quickly looking at it. It would take a little bit more work computationally to show that if I gave you, say, this matrix here that had maybe 1, 0, 1, 2, 3, 4, 1, 0, 1, that if we were to take the determinant of this 3 by 3 matrix here, because this row and this row are identical, and we know that if two rows or two columns of an n by n matrix are identical, then that determinant has to be 0. And we could show that by way of computation. But going forward, if ever you're asked to compute, say, a large determinant, and you end up with two identical rows or two identical columns, you can immediately say that that determinant will be 0. Okay, so let's look at this next one. This next property says that if I were to do any operation where I take one of these rows right here, and I replace it by a linear combination of it and some other row, that I do not change the determinant. So if I obtain this new matrix B by doing adding a constant multiple of one row to that other row, then we don't change the value of the determinant. So this would still be equal to the determinant of A. Let's see how that might be beneficial in this case. I'm going to create a new matrix in here by doing a linear combination of -2 times this first row, and I'm going to add it to the fourth row and replace that fourth row. So I'm going to say my R4 is equal to -2 row 1 added to row 4. So let's go ahead and do that computation. The first part stays identical. We have 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 8, 9, and then I'm obtaining this new row 4 here through this linear combination, and we end up with, when I multiply -1 or -2 by 1, that gives me -2. Add there gives me 0. If I multiply -2 to this 2, that gives me -4. Add to this gives me 0. -2 times 3 gives me -6. Add to that 6 gives me 0. And then -2 times 4 added to this 9 gives me a 1. And so what we're saying here is that these two matrices have the same determinant. We'll talk about, if you may already see something you can do here, we'll talk about that in this next line. So this is what you saw in your pre-work, that if we had the determinant of a triangular matrix, this could be upper triangular, lower triangular, or diagonal matrix, then the product of the entries is just the main diagonal of A. So for example, if I were to take the 4 by 4 identity matrix and I were to ask you to compute its determinant, what I'm saying is that for the determinant of this matrix right here, that's a 1 there. If we were to take this determinant of this 4 by 4 identity matrix, because this is called a diagonal matrix, it only has entries along the main diagonal, but that's a form of triangular matrix that I can just multiply those entries along the main diagonal. So the determinant of that identity matrix, and in fact the determinant of any identity matrix is 1. Okay? Let's look at the matrix that we just had up above here. This matrix that we just had above here, where we had the matrix 1, 2, 3, 4, 0, 5, 6, 7, 0, 0, 8, 9, 0, 0, 0, 1. If we were to take the determinant of this matrix, it is an upper triangular matrix. Sometimes that's just called a triangular matrix. Usually we mean upper when we say that. And because it's a triangular matrix, I can just multiply those entries along the main diagonal, making this computation much easier than it would be using the standard expansion by minors technique. What's really powerful about this, folks, is if you look at this problem here, we started out with a matrix that was not triangular. We did a row operation, but we know that when we could perform a row operation, this linear combination of two rows, that we don't change the value of the determinant in order to get a triangular matrix, and then we could just multiply the entries along the main diagonal. This gives us a much more efficient way to think about computing determinants of larger matrices. Finally, I'll just add this one just to make sure we've seen this example too. If I were to take, say, this matrix right here, 3, 0, 0, 2, 4, 0, 5, 0, 1, this matrix right here is lower triangular. Sometimes we'll just say it's triangular. And in this case, we can compute the value of the determinant by multiplying along these main diagonals, giving me a determinant of 12. So folks, that was a quick video that gave us an overview of a number of these determinant properties. And I like to think of them as sort of efficient properties that allow us to more quickly evaluate some of these determinants. Thank you very much.